Hi guys, this is a video on asymptotic efficiency, sometimes also known as Big O. The big idea that this concept deals with is that of scalability. Scalability is the ability of a computer system to handle large amounts of data or users. It's easy for a computer program to deal with just a handful of inputs, 5 or 6 things, but when we get to thousands or millions or billions of data points or users, that's when things may not scale up and the computer system might get too slow to be of any practical use. There's a mantra in software engineering called will it scale? So that involves asking this question. If we take this idea of yours, implement this feature, sure, it might work on a little test case on your personal computer, but would it scale up to the number of users or volume of data we would have in the real world? Scalability is teamwork between computer engineers who design computer hardware and software engineers who create computer software. We can't put the burden entirely on the hardware. We can't just expect faster and faster hardware to appear to handle scalability. Computer scientists need to also design data structures and algorithms that make efficient use of those resources. We need our data structures and algorithms to be fast too. The goal is to make scalability happen. That means we want these operations to be fast. In order to do that in a scientific way, we need to measure what's happening. So we measure the size of input into an operation as a number. We also measure the amount of time spent as a number. That's so that we can do a science-driven engineering process of optimization. We can consider changing something and then measure if it actually made things better. Did it actually make the operation faster? We can also predict how fast things will be, and that's part of the point of asymptotic analysis, or Big O. We can look at a particular operation and just think about it in our minds and predict scientifically whether that would be a fast thing or a slow thing. N is defined to be the number of inputs. This is just a convention. There's nothing magic about n, and n is not some mystical thing. N is just a math variable like x or y that represents the number of inputs into an operation. N is a pretty good letter for that number. We also measure the amount of time spent on an operation. The goal is to make this fast. So fast would be a small amount of measured time. So that would be a low number relative to n. What we do is we measure the amount of time spent as a function of n, the input size, and we want that to be a small number, to be a small amount of elapsed time. I just want to mention that's a little counterintuitive. We don't want high numbers. We don't want high speed numbers. When you're measuring how fast something goes in miles per hour or kilometers per hour, you want a fast number. But when you're measuring how quickly a goal is accomplished, like how fast a race is run, you want a low number. So here we want a low number. Lower is better. Here's a real-world example of an operation to try to make these orders of growth a little more concrete before we get into the data structure operation orders of growth. Let's consider the situation of class introductions. At the beginning of a face-to-face class, every student is going to introduce themselves to the rest of the class. N would be the input size. That's the number of students we're dealing with. The bigger the class, we would expect the longer this process would take. Time will be defined as the number of greetings that happen before we're done. One greeting is one student saying, here's my deal, this is me. Here's the first scenario we'll consider. Every student greets every other student, and we do this one at a time. So I'm the first student, I say, hello, classmate, hello, classmate, hello, classmate. I do that for the entire class, and then the next student does the same process. We have n students, each of them is making about n greetings. So the total number of greetings in that entire process would be n multiplied by n. I introduce myself to everyone, you introduce yourself to everyone, and so on. That's n multiplied by n, which we can abbreviate n squared time, quadratic time. Scenario 2 is each student introduces themselves to the entire class, and then they're done. So I introduce myself to everyone, then you introduce yourself to everyone, that proceeds. Here we have n students, each is making one greeting, so that's n times 1, which makes n number of greetings, n time. In general, that's a much smaller number than n squared. So we have better scalability. We're spending less time on this process. Finally, let's say we use some technology and every student sends a text at the same time. So I guess I'm the instructor. I say, students, I want you all to write a text and it will be rebroadcast to everyone. We can read the texts later. So all n greetings in the class happen simultaneously. There's just one unit of time that elapses. We wait for everyone to finish writing their text, maybe 5 minutes. Now we're done with the greetings. That's the best scalability because no matter how big the class is, the amount of time elapsed is the same. Here's a chart to show how the quadratic order of growth can get out of control pretty fast. I have some different student sizes. N is the number of students in a class. If we go with the texting scenario, scenario 3, no matter how big the class is, it just takes one time step to finish that process. If we go with the one at a time introductions, then we have linear scalability, so the time taken is just the same number as the number of students. That's pretty good scalability, and you can see even for a class of 30 or 100, 30 or 100 might be an amount of time we could conceivably spend on this task. The first scenario took n squared steps. This is not scalable. With a 5-student class that takes 25 greetings, which we might be able to sit through, but with just a 30-student class, we have to sit through 900 greetings, and that's way too much. That's not practical. People would get bored. We would go way over a 75-minute class. And with a 100-student class, it's 10,000. With 1,000, it's a million. Very quickly, this is getting out of control. So in general, this n squared order of growth is not scalable. It's usually too slow to use with large input sizes. What we're focusing here on is the order of growth. That means just big picture, how quickly does this time use scale up? We don't really care about minute differences. This comes from the turn of phrase on the order of. You might hear someone say something like, I got an unexpected dentist bill. Is it on the order of $100 or on the order of $500 or on the order of $10,000? There, I don't really care about the difference between $500 and $502. What I'm caring about is how big of an impact will this make on my life? So that's what we're concerned with. Some people say in the ballpark of. It's not as good a term because that relates to American baseball that not everyone in the world knows about. So let's say we modify the third scenario from my example. Instead of every student sending one text, they're going to send 2 texts. So that does make this process take longer. Now, instead of 1 unit of time, it takes 2 units of time. But that's the same order of growth. There's not a huge difference between people writing 1 text and people writing 2 texts compared to that n squared 1 million introductions kind of scenario. So the differences between n squared and n and 1, those are huge differences in order of growth. Those really matter to scalability. The difference between 1 and 2 doesn't really matter. So in this setting of analyzing asymptotic efficiencies and orders of growth, we don't care about constant factor differences, as they're called, the difference between 2 and 1 or 2n versus 3n time steps. We just don't care. Now we're ready to introduce an O expression. For the time being, we're going to be using a casual definition of big O. I have a formal mathematical definition soon, but the casual definition that we will use for now is that O of x is on the order of x, where x is an expression involving n. So what you write into this x spot is some mathematical expression involving n, such as n squared, the constant 1. There's a couple others we'll use involving logarithms that we'll talk about later. So in our example, we had big O of 1. That was everyone writes 1 text or everyone writes 2 texts on the order of a constant number of texts. We had big O of n, the linear scaling, and we had big O of n squared, the quadratic scaling. I want to mention, before we leave this topic, that there is a mathematical formal definition of big O. This is a well-defined mathematical object involving sound mathematics. However, that definition involves discrete mathematics and calculus. Those are math courses that data structures students haven't necessarily taken yet. So we don't use this formal mathematical definition. That's covered in a later class, Computer Science 335 Algorithm Engineering. So if you're into the formal sound mathematical approach, kind of wait for that course. We're going to be using that more casual approach.